तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we acquainted ourselves with the concept of transform diagrams and how they help us in writing down the equations of performance of a network in the Laplace transform domain. We took up this particular example where the switch S is closed at t equals 0 and we are asked to find out this current I. And then, taking note of the initial current in inductance to be 2 amperes, we replace that initial condition in the current by an equivalent voltage source in the transform diagram and we establish this transform diagram. As I mentioned in the last class, once we have the transform diagram, that can be analyzed in almost the same lines as what you would do in the case of DC circuits, writing down the various equations. We took up in the last class the loop current method for the solution of this network. We may as well use the node voltage method. We can use superposition technique, we can use Thevenin's theorem, whatever, all the whole gamut of techniques that are available, that is available for solution of DC circuits or AC circuits can be applied to the transform diagrams as well. Just for the sake of illustration, let me solve the same circuit by the node voltage method. Suppose I take this as the datum node, and if I solve for this node voltage, then I can find out the current in the 6 ohm resistor by dividing that voltage by 6. Therefore, I would like to use the node to datum voltage method. This is the node voltage to be solved for. Suppose this is the node 2, the value of this node voltage with reference to the datum is 10 by S, that is already known, and suppose I call this node 3, the voltage of node 3 to the datum is already known. So our aim is to write the node equations to solve for V1. So there is only one unknown node voltage, therefore let us say V10 of S times the sum of the admittances connecting that node. One admittance is, this is generalized admittance I am talking about, the impedance is 3, therefore the admittance is 1 by 3. The admittance of this combination, this whole entire branch, the impedance is S plus 2, therefore the admittance is 1 over S plus 2, plus the impedance of this is 6, generalized impedance, the admittance is 1 by 6. That is the self node admittance of node 1. Therefore, the mutual terms you have to take V20 of S and the admittance connecting nodes 1 and 2 is 3, therefore 1 by 3, therefore that is the coupling term that you are having. Further, you also have a coupling term with reference to 30 of S. So the admittance joining nodes 1 and 3 is 1 over S plus 2, so for 1 over S plus 2. This must be the sum of the currents entering node 1 through the various current sources. In this particular example, there is no such current source, therefore it is 0. Now in this equation, the only unknown is V10 of S, because V20 of S is known, that is equal to 10 by S. V30 of S is also known, since the polarity is plus with the 0 has positive polarity with reference to 3, V30 can be written as minus 2. On substitution of these values for V20 and V30, we can get V10 of S. V10 of S can be calculated and shown to be 6 times 4s plus 20 divided by 9s times s plus 4. But we are interested not in V10 of s, but the current in this 6 ohm resistance. Therefore, IFS is obtained by dividing V10 of s by 6, and when you do that, this becomes 4s plus 20 divided by 9s times s plus 4. 9s times s plus 4. This is exactly the same expression that we got for the current IFS using loop current methods, and once we have got up to this point, the further work is the same as what we have done in the case of loop current method. So, I will not do that. So, from this you can get I of t. The point is that once you have the transform diagram, you can analyze the transform diagram by any one of the known techniques that are available to you. In the whatever you do in the case of DC circuits can be applied to these transform diagrams as well, except in terms of resistances you have generalized impedances, except in terms of type DC voltage sources you have transformed voltage sources, instead of DC current sources you have transformed current sources. So, everything is in terms of S, but otherwise the principle, the technique is the same. Now, next question that we would like to ask ourselves is, how to deal with mutual inductance? We have so far addressed ourselves to finding out the generalized impedances of R, L and C elements. What do we do when we encounter mutual inductances? So, suppose I have two coupled coils having self inductances L1 and L2. These are the dot points and they have a mutual inductance M between them, and let me say the voltages and the currents of the two coils are indicated as follows, as given here. Then in time domain the equations of performance of this mutually coupled pair of coils is V1 equals L1 di1 dt plus M di2 dt, because the two currents, both the currents enter the dot points, therefore the sign of the mutually induced EMF is the same as the self induced EMF, therefore this is plus, that is also plus. V2 likewise is M times di1 dt plus L2 times di2 dt. These are straightforward standard equations governing the behavior of a pair of coupled coils, which you know. Now, when we transform these equations, term by term you transform. So, V1 will have Laplace transform V1 of s. When you transform this, this will be L1 times S times I1 of s minus I1 0. That is the Laplace transform of L1 di1 dt. Similarly, the Laplace transform of M di2 dt will be M times S times I2 of s minus I2 0. Second equation will be V2 of s M times S times I1 of s minus I1 0 plus L2 times S times I2 of s minus I2 0. So, this is a straightforward application of the transforming these equations. Now, we have to draw a transform diagram which depicts these equations. So, what you have now is V1 of s is L1s times I1s plus Ms times I2 of s plus minus L1 I1 0 minus M I2 0. Therefore, if I have in the transform diagram for the first coil, V1 of S is a transformed voltage, terminal voltage of the coil, and the coil has a self inductance L1 and it has got a generalized impedance L1 of S. This is self impedance of the first coil, and you have two sources, voltage sources representing the initial currents in the inductors. Therefore, this is L1 I10. Suppose I10 I write as rho 1 and I20 as rho 2 to simplify my notation. So, L1 rho 1 and minus Mi20, therefore, you have another term M rho 2. So, you have two voltage sources representing the initial currents in the inductors, and the second coil likewise will have a representation like this, where V2 of S is the terminal voltage and the current is I2 of S, and the Laplace transform of the current here is I1 of S, L2 of S, and then here you have once again minus Mi10, L1 of S minus I10, that is M times rho 1, and here you have L2 times rho 2. In addition, we have a coupling impedance Ms here. So, that means once we have write down this equation, the transform diagram in this fashion, we say the voltage, terminal voltage V1 of S of this coil is I1 of S passing through L1 of S will create a drop L1 of S times I1 of S. In addition, I2 flowing to this coil will have a mutually induced voltage here, whose Laplace transform is Ms times I2 of S. So, you have not only L1 of S, L1S times I1 of S, plus also Ms times I2 of S, L1 of S, I1 of S plus Ms times I2 of S. In addition, representing the initial currents in the inductors, we have two voltage sources. Likewise, the same situation is there in the second coil also. This is very similar to what you do in the case of steady state circuit analysis, AC circuit analysis, where instead of the self inductance is represented as an impedance J omega L1. The mutual impedance is J omega M. So, instead of J omega we have S, otherwise it is exactly the same that the situation that you have in the case of AC circuits. Now, you may as well think of replacing the initial currents through current sources. So, if you do that, you can write this equation in this form. You can write V1 of S, you can write as L1S times I1 of S minus rho 1 by S. So, instead of writing minus L1 rho 1, I can write L1 of S times minus rho 1 by S. So, this term here is put in this form, plus Ms times I2 of S minus rho 2 by S, and you can write V2 of S exactly going in the same method, Ms times I1 of S minus rho 1 by S plus L2 of S times I2 of S minus rho 2 by S. That is what we are having. So, if you look at these two equations, you can represent them in this fashion. You can have a current source here. So, let this current source be of strength rho 1 by S. So, the current in the actual inductor here is I1 of S minus rho 1 by S, and that current passing through L1 of S will set up a voltage drop L1 of S times I1 of S minus rho by S. In addition, you have a mutually induced voltage Ms times the current in this coil. And what is the current in that coil? In a symmetrical way, you have I2 of S here, this is V2 of S, and you have another current source here which is rho 2 by S. So the current in this coil is I1 of S minus rho 1 by S, and the current here is I2 of S minus rho 2 by S. So now we see that this voltage V1 of S is obtained as the drop in this inductor. What is the drop in this inductor due to self-induced EMF? I1 of S minus rho 1 of S times L1 of S, and the mutually induced voltage is MS times the current here, which is I2S minus rho 2 by S. So these are exactly the terms that we are having here. Similarly, the voltage induced in this, which is equal to V2 of S, is the self-induced voltage I2 of S minus rho 2 by S times L2 of S, and the mutually induced voltage, which is MS times I1 of S minus rho 1 by S. That is the one. So these are two alternative representations of the initial conditions in a mutual inductor. If you are in love with voltage sources, you use this diagram. If you like to use current sources, you can use this diagram. The advantage with the current source representation is that on one side you have only rho 1 only figures here, whereas here when you put the voltage source, both rho 1 and rho 2 come on both sides. That is a minor advantage. So this is the way in which we can analyze the transient problems involving mutual inductances. Let us work out an example to clarify these ideas. In this example, we have a circuit with a pair of coupled coils having the following having this arrangement: 2 Henries, and let this also be 2 Henries self inductance, and let the mutual inductance between these two coils be 1 Henry. Let the element values be as marked here. These two are current sources, DC current sources, 1 ampere and 2 amperes, and the switch is kept open for a long time and closed at t equals 0. You are asked to find I2 of t. Find I2 of t for t greater than 0, greater than or equal to 0. So let us see, as far as this inductor is concerned, it does not carry any initial current at t equals 0 because the switch is open. Therefore, if we call the rho 2 to be the current here, it is 0. As far as the first inductor is concerned, this 2 ampere current source, DC current source, flows entirely through this inductance because under steady state the voltage here is 0. Therefore, this 2 ohms is short circuited. Therefore, rho 1 is 2 Henries. So from the statement of the problem, we know that rho 1 is 2 amperes, that is the current in this inductor at t equals 0 minus the current in the second inductor is 0 amperes. So that is what we are having. So if you set up the transform diagram for this, you have corresponding to the 2 amperes DC source, you have 2 by S, that is the current source in the transform domain, and you are having 2 the generalized impedance of this resistor, and you are having self inductance 2S, and since the initial current here is 2 amperes, I can replace this by an equivalent current source of 2 by S in the second representation which we have just now discussed. And these two inductors have the same self inductance and a mutual inductance which is equal to S in the transform domain, and once the switch is closed here, you have this 2 ohms and then the current source here. You should not put the current source as 1 here, but 1 by S because that is a DC source and we are talking about the transform domain. All the variables here are transformed variables. Now in this we are interested in finding out I2 of S. This is the what we are after. Observe here that 2 by S and minus this 2 by S coming together at the same node cancel each other out. That is, if you have a current source here of some amp, say Ix, and another current source of Ix here, So they both of them cancel each other out, and therefore the net current in the whatever to which is connected is 0. So using this principle here, after all this current source and this current source are parallel to each other and equal and oppositely headed. So their effect on the rest of the circuit is negligible, is 0. Therefore I can write this simply as 2, this is 2s, and a coupling of s between these two, and you have 2fs, and you have 1 by s as the current source. This is 2, this is 2s. So that is what we are having. So we can suppose I like to use the loop current method of analysis. They can convert the current source in parallel with a resistance as a voltage source in series with a resistance. So this is equivalent to 2 ohms, 2s, this is 2, again generalized impedance 2 ohms, 2s, coupling term of s. Now a current source in parallel with a resistance can be replaced by an equivalent voltage source in series with a resistance, and the strength of the voltage source, just as you use Thevenin Norton equivalents that in DC circuits, the multiplication of these two, this becomes 2 by s. So you have a voltage source 2 by s in series with a generalized impedance 2. So if I write the two loop equations as loop currents as I1 and I2, the current here is what we are interested in, that is the same as I2, the current in this coil. Therefore the identity of that current is retained, and you write the loop equations for this. So I can write this as 2s plus 2. I write these loop equations in matrix form because they are quite simple and easy to visualize. So I write this I1 of s and I2 of s, and on the other side I write the forcing functions. Therefore the first loop equation is 2s plus 2 times I1 of s, 2s plus 2 times I1 of s, and this the mutually induced voltage I1 is entering the dot point and I2 is leaving the dot point. Therefore the sign of the mutually induced voltage is negative, and the multiplication factor is s because this is the mutual impedance. S times I2 is the magnitude of the mutually induced voltage, but we have to have a negative sign, therefore minus s times I2 of s, and the total driving voltage in this loop is 0. Now for the second loop, the self-induced the self-impedance of this loop is 2s plus 2, and the mutually induced voltage, again I2 is leaving the dot point and I1 is entering the dot point. Therefore the sign of the mutually induced voltage is negative. The mutually induced voltage has a Laplace transform s times I1, but the sign is negative, therefore minus s times I1 plus 2s times I2 of s. That must be the net voltage in this loop trying to drive a current in the direction of I2, but the total EMF in the circuit is 2 by s in the opposite direction, therefore I must write this as minus 2 by s. So these are the equations which describe the behavior of this circuit on the loop current basis. You can solve for this and you get an expression for I2 of s. The solution of these two equations will give you I2 of s equals minus 4 upon 3 s plus 1 over s times s plus 2 by 3 times s plus 2, which on partial fraction expansion will yield minus 1 by s plus half divided by s plus 2/3 plus half s plus 2. So that is the partial fraction expansion of I2 of s, and therefore you can write I2 of t as minus 1 plus half e to the power of minus 2t by 3 plus half e to the power of minus 2t, and the entire quantity is of course multiplied by ut. That is the expression for I2 of t. So you can see that the solution for the transient problem of this sort, once again can easily be handled with the transform diagram approach. You do not have to write the differential equations, and once you have the transform diagram, you write the equations of performance in S domain in the same way as you would do for DC circuits, and once you get the solution for the required quantity in terms of transforms, you have to find the inverse transform to find the pertinent quantity in time domain. Let us now consider another example in which the Laplace transform technique is applied to a circuit containing sinusoidal sources. So you have a sinusoidal voltage source of 10 sin omega t as the voltage, and the switch is closed at t equals 0. Let there be two elements in the circuit, R and L, and we are interested in finding the current in the circuit for t greater than or equal to 0, and it is given that I0 is rho. Because of some previous switchings, previous arrangement, the current in the inductor is I0 at the time of switching. So we make the transform diagram for this. So the voltage source has a transform 10 omega over S squared plus omega squared. That is the Laplace transform of 10 sin omega t. And you have a resistance R, that is the generalized impedance of this. As far as the inductor is concerned, you have a generalized impedance Ls, and in addition you have a voltage source representing the initial current in the inductor, which is rho times L. The voltage of that voltage source is rho times L rho. So that is what we are having. So that completes the transform diagram, and in this we are interested in finding out the current IFS. So if you write this, after all this is a simple single loop circuit, therefore IFS can be written as 10 omega over S squared plus omega squared plus L rho, that is the total driving voltage in that loop, divided by Ls as R, that is the total impedance in the circuit. Now this can be written as, after all you have to make the partial fraction expansion for this. So I can write this as, first of all, L rho over Ls plus rho, that is straightforward, therefore I get rho over S plus R by L, that comes from this, plus in addition I have 10 omega over S squared plus omega squared, the first term, the ratio of the first two terms. I will write S plus R by L and divide this by L. So 10 omega over L divided by S squared plus omega squared times S plus R by L. So if you make the partial fraction expansion of this, you will get rho over S plus R by L as before for the first term, and for the second term you have S plus R by L, one term, and that will turn out to be 10 omega L divided by R squared plus omega squared L squared. You can carry this out. I do not spend time in working out the details, but one can easily arrive at these values. And you have, for the S squared plus omega squared term, 10 omega R over R squared plus omega squared L squared divided by S squared plus omega squared minus 10 omega L divided by R squared plus omega squared L squared times S over S squared plus omega squared. Actually, when you have S squared plus omega squared in the denominator, you have AS plus B times in the numerator. I split this up into two portions so that this can be recognized to be the Laplace transform of a sine function, this case recognized to be the Laplace transform of a cosine function. So IF t is, for the first time is concerned, rho e to the power of minus RT over L. rho e to the power of minus RT by L. That is the Laplace transform of this. As far as this is concerned, you have 10r by r square plus, right, let me say 10 by r squared plus omega squared L squared, that is a common factor right through, so I will keep that separately. 10 by r squared, you have omega over s squared plus omega squared gives you sin omega t, therefore you have r sin omega t. Here again 10 over r squared plus omega squared L squared has been taken out. S by s squared plus omega squared will yield me cos omega t, therefore I have minus omega L cos omega t plus, here 10 by r squared plus omega squared L squared is taken out as a common factor, therefore plus omega L times e to the power of minus RT by L, and of course u of t. So this is your, all this is multiplied by u of t. U of t. You notice that at t equals 0, this is 0. This cancels out with this because cos omega t and e to the power of minus RT by L are both equal to 1. This is 0. Therefore, this term is 0 and this is equal to 1, and the initial value of the current IT is rho, which is what we know. Now in this you observe that this term and this term can be combined if you wish. It is a decaying transient minus RT by L. Therefore, this term and this term together are the transient terms. They decay with time. Actually, both of them can be combined. Whereas these two terms are the steady state terms. You are driving this particular circuit with a sinusoidal forcing function, therefore there is a steady state solution, and this is what we are having. You can show this steady state term to be 10 by root of r squared plus omega squared L squared, that is the impedance of the circuit, sin omega t minus theta, where tan theta equals omega L over r. So this is the steady state solution. You have here an AC circuit in which you have a driving force 10 sin omega t, and you have a r and L in the circuit, therefore the impedance is square root of r squared plus omega squared L squared, and the power factor angle equals tan inverse of omega L over r. So that is the steady state solution. You combine these two and you can show very easily that the sum of these two is indeed this. The transient part of the solution equals rho plus 10 omega L over r squared plus omega squared L squared e to the power of minus RT over L. That is the transient part of the solution. Rho e to the power of minus RT by L plus 10 by r squared plus omega squared L squared times omega L e to the power of minus RT by L. This is the transient solution. So in this we can see that once we have a solution, we can identify the terms which correspond to the steady state behavior of the current and what are the terms which correspond to the transient portion of the response. So both these are simultaneously brought out in the final solution. You can combine these terms and show it to be so. And of course, once you have the total solution that is valid only for t greater than or equal to 0, therefore u of t will always be there to specify that I of t, that expression whatever we have, is valid only for t greater than or equal to 0. Let us work out one more example. Let us now consider this example which we had earlier discussed in the context of the classical method of differential equation approach to the solution of transients. We have a setup here in which the two inductors, the two inductors were originally carrying different currents, but once the switch is opened, both of them are perforce required to carry the same current. Therefore, this is a case of discontinuous inductor currents in the transition from t equals 0 minus to 0 plus. In the case of differential equation approach, we have calculated the t equals 0 plus conditions separately. Now let us use the Laplace transform method and show that once you substitute t equals 0 minus conditions, 0 plus conditions almost immediately follow in the normal routine you do not have to make separate calculations. So let us use 0 minus conditions and solve for this circuit. You recall that the current was originally 3 amperes in the, when the switch was closed, the current in the IL1 is IL1 0 minus is 3 amperes and IL2 0 minus was 0 amperes. But once the switch is opened, IL1 0 plus and IL2 0 plus are going to be the same, and we would like to know what this value is, and we use the constant flux linkage theorem or some similar effect to find out the current, the new current in the inductors. Let us use Laplace transform techniques here. So let us draw the transform diagram for this. You have 12 by S is the transform of the voltage source. You have 4 2S, and as far as the inductor is concerned, we use the I 0 minus values. 0 minus values 3 amperes, so 3 times 2 6. L1 IL1 0 minus, that is 6, and down here you have inductance of value S, impedance S, and the initial current is 0, t equals 0 minus, therefore you may as well do not have that, and you are having 4 ohms. So what is the current here? This is a very simple circuit. So I of S is will be 12 by S plus 6 divided by 3S plus 8. That is what you are having. So that this will be 2S plus 4. You simplify this, you get 2S plus 4 times S plus 8 by 3. S plus 8 by 3. Now we can make the partial fraction expansion, find out the I of t, but before that let us find the initial value of the current. I0 plus equals limit as S tends to infinity of S times I of S. So when you multiply this by S and take the limit as S tends to infinity, that becomes 2S squared by S squared, therefore this is 2. That means this current from 3 amperes has jumped to 2 amperes at t equals 0 plus, and something else it goes like this. So automatically you find out the I0 plus. So if you want to find IT separately, you make the partial fraction expansion, this becomes 3 by 2S plus half of S plus 8 by 3. So you get I of t in the loop as 3 by 2 plus half of e to the power of minus 8t upon 3 u of t. So that current was originally 3 amperes in IL1 has jumped to 2 amperes, and then finally it decays to 3 by 2 amperes. Now what about the inductor voltage? Suppose I want to find out the inductor voltage VL1 of S. When you want to find VL1 of S, now that we have got I of S, 2S times I of S plus, that is the drop here, minus 6. So when you want to find the inductor voltage, you must take the voltage between these two terminals, not across this inductor alone, this portion only. You must take the initial source, initial current source also into account, because these are now the terminals of this inductor in this circuit. This inductor has been replaced by not only an inductive impedance but also the initial current source. So when you want to find out VL1 of S, if this is VL1 of t, the corresponding Laplace transform is the voltage in the transform diagram existing between these two terminals. You should not make the mistake of computing only this portion. So 2S times I of S minus 6, that is VL1 of S, and you can show that this will be minus 2 minus 8 by 3 e to the power minus 8 by 3 divided by S plus 8 by 3, which means VL1 of t is minus 2 delta, I will write this separately here, VL1 of t is minus 2 delta t minus 8 by 3 e to the power of minus 8t by 3. And likewise, if you calculate VL2t, that is the voltage across this between these 2 points, VL2t, likewise if you calculate, you will get the result 2 delta t minus 4 upon 3 e to the power of minus 8t upon 3. So, since both the currents have jumped from t equals 0 minus to 0 plus values, you no doubt there will be impulse functions, but taking the L1 and L2 put together, the impulse functions cancel each other out. That means even though inductors have impulse voltages in them, in the local loop the impulses get cancelled. Therefore, all the other voltages are finite, and therefore the total Kirchhoff's voltage law is still satisfied, because the impulse voltage generated here is cancelled by the impulse voltage generated here, because this will be now VL2 of S, this is VL1 of S between these 2 points, and the sum of these turns out to be 0. So, we have worked out a number of examples illustrating the Laplace transform technique. As I mentioned, once we have the transform diagram, we can use the whole range of network analysis techniques that is available to us in the context of DC circuits or AC circuits. We can use the node analysis, the loop current method of analysis, superposition, the various network theorems we can apply. All these follow in a straightforward routine fashion. Later on, we will return to a discussion of network theorems at some point, and then we can pick up this thread at that time. But at this time, from what we have seen, let us now see what are the advantages of the Laplace transform domain in the transient analysis of electrical networks. We find there are a number of advantages compared with the classical differential equation approach. First, when you have functions of time which are discontinuous or which have discontinuous derivatives, like your step function or ramp function, then the Laplace transforms of these time functions turns out can be simple expressions, whereas if you look at the classical differential equation, suppose you have the function is described by different analytical expressions in different regions of time. So, you have to find the solution for one interval of time, find the final solution, and fit this up as the initial condition for the next interval, and so on and so forth. That becomes quite complicated, whereas in the transform domain, for the entire range of time, you have one single simple expression for in the Laplace transform domain. Secondly, we observe that we do not have to involve ourselves with calculus operations, no integration, no differentiation. All the equations describing the behavior of the system are put in purely algebraic form, algebraic equations are involved. So, calculus is converted into a kind of algebra, because differentiation corresponds to multiplication by S, integration corresponds to division by S. So, calculus is converted to algebra. A third feature is that you get the total solution, the transient part of the solution and the steady state part of the solution both together in one unit, whereas in the classical differential equation you have the particular integral solution, the complementary function. So, they are found separately and you combine them, but here you do not have to do that. You find out the total solution in one step, but once you have got the total solution, you can identify the steady state part and the transient part in the final solution using common reasoning, which is, and these terms will become evident if you see what are the terms which correspond come from the forcing function and what are the terms which come from the system itself. This will be made more clear when we discuss the system function and its ramifications later on. But the main advantage of the Laplace transform technique is that the initial conditions pertaining to the system are plugged into the solution, into the equations at the very beginning itself. Therefore, you do not have to evaluate separately the arbitrary constants that you have to do in the case of differential equations. And this is very important, because if the order of the system, the number of reactive elements becomes large, suppose there are 4 or 5 reactive elements and you have a 4th order differential equation, then you need to know 4 initial conditions, not only the initial value but the values of the first 3 derivatives. and this becomes quite complicated because they are not evident, they are not given with the problem, and you have to calculate this. You have to find out the initial derivative, the second derivative, the third derivative through separate manipulations. All that is unnecessary as far as the Laplace transform technique is concerned. All the initial conditions pertinent to the reactive elements are used in the transform diagram, or equivalently in the differential equation. You substitute them and you get the solution. So separate evaluation of arbitrary constants is not necessary at all in the transform approach. And in this context, it is also seen that you do not have to find out the 0 plus conditions separately from 0 minus conditions. If you have 0 minus conditions, you straight away plug them in. You use 0 minus conditions, and the solution that you get is one that starts from 0 minus. Automatically it will proceed, and if in fact if you are interested in finding out 0 plus conditions, you can use the initial value theorem, the final expression, and find out what the 0 plus conditions are. So all these are the advantages of the transform approach to the solution of transients in networks. To summarize once again, because this is a very important aspect, let me recapitulate the various advantages that we have mentioned. First of all, functions which are discontinuous and which have discontinuous derivatives are easily handled in the transform domain because you get one single expression valid for all time. Secondly, we find that calculus is converted into algebra, so the manipulations are that much easier. Thirdly, we find the transient and steady state solution come together in one package, but you can separate them at the final solution into the two separate components if you so wish. And most important of all is the fact that the initial conditions are used in the problem to start with. The data regarding initial conditions is fed into the problem in the very beginning itself, so separate evaluation of arbitrary constants is avoided. This is a troublesome feature as far as the classical differential equation solution is concerned. After having said all this, you must also be fair to the fundamental approach of differential equations. What is it that differential equations can do which Laplace transform perhaps cannot do? See, the differential equation solution is a very fundamental solution, fundamental approach. Suppose you have given some data, not the initial conditions at t equals 0, but you specify some conditions and the response. Initial value equals so much at t equals 0. The derivative is equal to so much at t equals 1 second. The second derivative is so much at t equals 2 seconds. Suppose the data which regarding the arbitrary constants are specified in a different way, not all at t equals 0, then the Laplace transform domain is not very convenient to handle such type of data. If all the initial conditions at t equals 0 are given, then it is nice. But if it is not so, then the differential equation is much more amenable to giving us the proper solution and it certainly is a more fundamental approach. So one will also have to keep in mind, one should also know how to handle transient problems using the classical differential equation approach. Even though Laplace transform has a lot of advantages and we for the most part resort to Laplace transforms, one should not completely ignore or forget the differential equation approach to the solution of the transient problems. Particularly in very simple cases, you can write down the differential equation solution by mere inspection. You do not have to transform those equations every time. So it's a powerful technique, no doubt, but in very simple cases the straightforward application of differential equations will fetch you the result quickly and also with a little bit of insight into the working of the problem. So we have covered in these last two lectures the application of Laplace transforms to the transients in networks. Now in the next lecture we will take up the question of how to use Laplace transform technique to general analysis of a system. We go back to the system function that we already talked about in our preliminary set of lectures and see how you connect it up with the Laplace transform technique. This will be the topic in the next lecture.